Welcome, my friends. Consider the function f of x is equal to 2x plus 5. We could create a table of values to evaluate various inputs into this function. If we plug in x is equal to 0, we will get 2 times 0 plus 5, which is equal to 5. If we plug in x is equal to 1, we will get out 2 times 1 plus 5, which is equal to 7. If we plug in x is equal to 2, we will get out 2 times 2 plus 5, which is 9. If we plug in x is equal to 3, we will get out 3 times 2 plus 5, which is 11. We can express the input-output relationship as ordered pairs, so that we have 0, 5, 1, 7, 2, 9, and 3, 11. The first value in each ordered pair represents our input of x, and the second value represents the output of f of x, sometimes labeled as y. Now imagine that there is some function out there that goes backwards. What I mean is, each of the x values of 0, 1, 2, and 3 are inputted into this function to get the values 5, 7, 9, and 11. But is there some function out there that takes the y values as inputs and outputs the x values? In other words, is there a function out there that switches the values for x and y around? And if so, how can we find such a function? Well, it turns out that this function exists, and it is called the inverse function. The inverse function undoes a function. That is, if you input the y values, or the outputs, from the original function, you will get back the x values that were initially inputted. To find the inverse function, first rewrite the function with y instead of f of x, as f of x represents the outputs, or the y values. Then you need to switch the x's and the y's, as that is what an inverse does. Finally, solve the new function for y, and you will have the inverse. For example, we have the function f of x is equal to 2x plus 5. Let's rewrite this as y is equal to 2x plus 5. Now let's switch x and y, so that we have x is equal to 2y plus 5. Now solve for y. Subtracting 5 from both sides, we have x minus 5 is equal to 2y. Dividing each side by 2, we have y is equal to x minus 5 divided by 2. Now, note that the y in this function is not literally the same y from f of x. We switched x and y around because x is traditionally thought of as the input in any function. Oftentimes, the inverse function is represented by f negative 1 of x, so we might rewrite our function as f negative 1 of x is equal to x minus 5 divided by 2. From here, you can test to see if this truly is the function we wanted. We want a function that inputs the y values and outputs the x values. For example, we know that we had the point 2, 9 on the original function, so we should have the point 9, 2 on the inverse function. If we plug in 9, we get f negative 1 of 9 is equal to 9 minus 5 divided by 2, which is equal to 4 divided by 2, or just 2. This verifies that when we plug in 9, we do indeed get 2. You could try this for a few other numbers, but know that you will always get the x value from the original function back when you plug in a y value into this function. Let's try another example of finding the inverse. Say we have f of x is equal to x plus 4 divided by 5, and we want to find the inverse. The steps are to first replace f of x with y, so that we have y is equal to x plus 4 divided by 5. Next, switch x and y around so that we have x is equal to y plus 4 divided by 5. Now solve for y. Multiplying both sides by 5, we have 5x is equal to y plus 4. Subtracting 4 from both sides, we have y is equal to 5x minus 4. Next, replace y with f negative 1 of x, so that we have the inverse is equal to 5x minus 4. Any ordered pair x, y from f of x will translate into a point y, x in f negative 1 of x. Now, something interesting about inverses, which makes complete sense when you stop to think about it, is that a function composed onto its inverse will always be equal to the input. For example, f of f negative 1 of 2 is the same thing as f of f negative 1 of 2. If you evaluate this, you will get 2. The reason is that a function and its inverse undo each other. So whatever f negative 1 of 2 is, f of x will take it and convert it back to 2 if f of x and f negative 1 of x are truly inverses. Don't believe me? Let me show you. F negative 1 of 2 is equal to 5 times 2 minus 4, which is 10 minus 4, or just 6. We should be able to plug 6 into f of x and get back the original input of 2. We have f of 6 is equal to 6 plus 4 divided by 5, which is 10 divided by 5, or 2, confirming my original statement that f of negative 1 of 2 would be equal to the input of 2. Hopefully you are able to see what's happening. The point 2, 6 is on the inverse, and the point 6, 2 is on the original function. If you plug 2 into the inverse, you will get out 6. And then if you plug in 6 into the original function, you will get back 2. So whatever the inverse does, the original function will just undo it. So whenever you have f of negative 1 of x, the answer should be the input, which is just your x value. This also works in reverse. So if you have f of negative 1 of f of x, that should also equal x. So the way that you can verify that two functions are inverses are if their composition results in the input. A bit more formally, you can tell if two functions, f of x and g of x, are inverses of each other if both f of g of x is equal to x and g of f of x is equal to x. There is also technically the stipulation that this only needs to be the case within the domain of g in the first condition and within the domain of f within the second condition. Consider the two functions f of x is equal to negative 2x and g of x is equal to negative x over 2. We would like to see if these two functions are inverses of each other. First, let's check f of g of x, which should be equal to x if the two functions are inverses. We have f of negative x over 2, which equals negative 2 times negative x over 2. The negative sign and the 2 cancel, so that we just have x, which is consistent with the two functions being inverses. But we do still need to check g of f of x to see if that is also equal to x. Checking g of f of x, we have g of negative 2x. G of negative 2x is equal to negative 2x divided by 2. The negatives cancel, as well as the 2's, and we are left with just x. As f of g of x and g of f of x are both equal to x, f of x and g of x are inverses of each other. Now, not all functions have an inverse. Consider the function f of x is equal to x squared. If we were to make a table of inputs, we could have these values: negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. We could have more points, but this is enough points to see the idea. The inverse of a function should take the outputs and return the inputs. But we have a problem here. There are multiple outputs associated with many of the inputs. For example, the output of 4 can be generated both with an input of 2 and with an input of negative 2. The output of 1 can be generated both with an input of positive and negative 1. The inverse function needs to be a function, meaning each input can only have one associated output. As there are multiple inputs associated with many of the outputs in f of x is equal to x squared, this function does not have an inverse. More specifically, we say that a function must be one-to-one in order to have an inverse. A function is a one-to-one function if each input has exactly one unique output. X squared is not a one-to-one function as there are many inputs that produce the same output, such as 2 and negative 2 both outputting 4. The output of 4 is not unique to any one input. The output of 4 is common to multiple inputs, making x squared not a one-to-one function, which is why it does not have an inverse. Now, don't confuse being a one-to-one function with simply being a function. Remember that to be a function, each input must have exactly one output, but the outputs don't necessarily need to be unique in a function. Graphically, you might remember that a function passes the vertical line test. We have a function if no vertical line intersects more than one point. So y is equal to x squared is a function as no vertical line crosses more than one point. a function is 1-to-1 if it passes the horizontal line test, meaning no horizontal line intersects more than one point. We can draw many horizontal lines through the graph of x squared, which will intersect more than one point, indicating that f of x equals x squared fails the horizontal line test, and therefore is not a 1-to-1 function, meaning it will not have an inverse. Let's look at the function f of x is equal to 5x minus 8 divided by 4x plus 7, which we would like to find the inverse for. To find the inverse, we first replace f of x with y, so that we have y is equal to 5x minus 8 divided by 4x plus 7. Next, we switch the x's and the y's in our function, so that we have x is equal to 5y minus 8 divided by 4y plus 7. Now we must solve for y. Let's multiply both sides of the equation by 4y plus 7. We have 4y plus 7 times x is equal to 5y minus 8. Distributing the x, we have 4xy plus 7x is equal to 5y minus 8. Let's get the y terms onto one side of the equation and everything else to the other side. We can do this by subtracting 5y from both sides and also subtracting 7x from both sides. This leaves us with 4xy minus 5y is equal to negative 8 minus 7x. Now we can factor out a y from the left-hand side so that we have y times 4x minus 5 is equal to negative 8 minus 7x. Finally, we can divide both sides by 4x minus 5 so that we have y is equal to negative 8 minus 7x divided by 4x minus 5. We can replace y with f negative 1 of x, so that we have f negative 1 of x is equal to negative 8 minus 7x divided by 4x minus 5, which is our inverse function. So our two functions are f of x is equal to 5x minus 8 divided by 4x plus 7, and f negative 1 of x is equal to negative 8 minus 7x divided by 4x minus 5. What is the domain of the inverse function? Well, we can have any value such that the denominator is not equal to 0. So we can set 4x minus 5 equal to 0. Adding 5 to both sides, we have 4x is equal to 5. Dividing both sides by 4, we get x is equal to 5 over 4. The domain of the inverse includes all values except x is equal to 5 over 4, or in interval notation, negative infinity up to 5 over 4, union 5 over 4 up to infinity. What about the range of the inverse function? The range can be a bit trickier to find sometimes, but since the x and y values switch in any inverse function, it also should make sense that the domain and range will switch around, as the domain includes all inputs, or x values of the function, and the range includes all outputs, or y values of a function. So the range of the inverse should be equal to the domain of the original function, f of x. The domain of f of x will be restricted so that the denominator is not equal to 0. That means 4x plus 7 can't equal 0. Setting 4x plus 7 equal to 0, we can subtract 7 from both sides to get 4x is equal to negative 7. We can divide by 4 to get x is equal to negative 7 over 4. The domain of f of x is all values such that x is not equal to negative 7 over 4. In interval notation, we have negative infinity up to negative 7 over 4, union negative 7 over 4 up to infinity. Since the domain of the original function matches the range of the inverse, this also must be the range of the inverse function. Okay, let's try a word problem involving inverses. Say Luke is walking from his home to the park. His distance from the park in meters after t minutes of walking is given by d of t is equal to 1,500 minus 100t. How would you describe what the inverse of d of t calculates? Well, we know that the function d of t inputs a time in minutes and outputs a distance in meters. So the ordered pairs would be t, d. The inverse must do the opposite, meaning it must take a distance and output a time. So the points on the inverse would be d, t. In words, the inverse of d inputs the distance Luke is from the park and outputs the amount of time he has spent walking. Let's find the inverse of d. The original function is d of t is equal to 1,500 minus 100t. Usually, we replace f of x with y, but here we need to replace d of t with d. we have d is equal to 1,500 minus 100t. Now usually we would switch our variables around at this point to represent that the inputs and the outputs are switching around. But since d and t stand for specific variables in this problem, we don't need to switch d and t around. We can simply solve for t with the function that we have. Subtracting 1,500 from both sides, we have d minus 1,500 is equal to negative 100t. Dividing both sides by negative 100, we have t is equal to d minus 1,500 divided by negative 100. This can be written as t is equal to negative d minus 1,500 divided by 100 if we bring the negative out front. We could write this as t of d is equal to negative d minus 1,500 divided by 100. This is the function that outputs the time in minutes Luke has been walking if he is d meters from the park, which is the inverse of the initial function d of t. For example, if Luke is 500 meters from the park, then d is equal to 500, and we have t of 500 is equal to negative 500 minus 1,500 divided by 100. This simplifies to negative 1,000 over 100. The negatives cancel, and we have 10. If Luke is 500 meters away from the park, he must have been walking for 10 minutes. Alright, my friends, that completes our video covering the inverse of functions.